This video segment is about doing harmonic analysis, harmonic dynamic response in Catia. First, let me give you an idea of what this is about. In all likelihood, if you're doing FEA and you're watching this video, you probably already know, but that's for the sake of the people who don't know what's going on. Suppose we have a bar and it's axially loaded, but it's loaded under a harmonic condition. In other words, it's a sinusoidal or cosinusoidal loading, like that. Okay. So from the basics of dynamics, we know that if this load is harmonic, the response at any point is also going to be harmonic. It's going to have certain amplitude as a function of time, and of course a phase angle. It could be that the motion of this point is lagging or leading the way the load is applied, and so the whole idea of harmonic analysis or dynamic response or frequency response is to find out at a particular location what is the value of x naught for a given frequency omega, for a given frequency omega, big omega, what is the magnitude x naught and what is the phase. Now I'm not going to worry about the phase, but I'm going to worry about the magnitude here. So the problem is exactly the same geometry that we had. We're not going to model this thing with beam, we're going to do it with bar. Of course, beam and bar are the same. One carries axial load, the other one carries bending load. So let's go ahead and make this thing and see what's going on. Alright. Oh, before I do that, I want to point out that notice that there is a peak here. This peak does have a significance, as you will see later. Okay, so let's start with a part file. Okay, on that vertical plane, I will sketch a line that's 20 inches long. I've seen this so many times now. It's probably you're sick of it, but okay. So this is going to be 20 inches. Okay, exit. Do not forget to join this because otherwise you will not be able to mesh it with beam element. Now I'm going to create a point here because we're going to be monitoring that middle point, for example. That's at 10 inches long. Alright, the load is applied at the end, so I don't have to worry about it. Exit. Did I apply material? No, I haven't applied material to it. So let's apply material. Metal on that part, we make it out of steel, and we slightly change the values here to match that thing that I had before, although we're not comparing it with any results, so it really doesn't matter. But to be consistent with what we did, 30 and 7.4 here. Slit per inch cube. Okay, good. Now we're going to go to generative structure analysis. Let's do a static analysis first. Try to measure it. Mesh this. The problem is, as I mentioned in the earlier video segments, I can mesh this thing, but there's no guarantee that there's going to be a point, a node at that location. So we're not going to do this thing here. If you want to do any fancy things with meshing, so you go to advanced meshing tools, right? Advanced meshing tool. Click on the beam mesher. Notice that this stuff was not in the in the dialog box that you were getting for generative structure analysis. So the size of the element is good, and I want to make sure that point is included in my notes. Okay, and then say OK. And we're done here. So now we're going to go back to generative structure analysis. Let's change this element type from a beam to a bar. Change type. Let's change it to bar. Okay. And give it the properties. Now we don't have a beam anymore. We have a bar. And we click on the wrench. And the area of that thing is 1 inch squared. I don't have to worry about I because it's not on the bending, and the support is right here. Okay. and we close that. All right. Now this end is clamped right there. Okay, and this end is subjected to a load of 100 cosine omega t. But for now, I'm going to do a static load. Where is the static load? Where is the load, distributed load at that point? In the direction x. 100. There you are. You can see that? The load is right there. Okay, good. Why don't we go and save the stuff? File, save management, analysis, save as. I think this folder that I had was called frequency response. So okay, automatically it's going to save the part 2. Now we run this thing, but nothing fancy is going to happen because all that happens is that the beam is going to stretch. Sure, and right there you see the biggest displacement at the tip, of course, and zero displacement at the clamp. Okay, so now remember we are doing linear dynamics. It's either harmonic or transient. We're doing harmonic, but the first step for doing those is you have to do a frequency analysis, because remember Catia's dynamics capability is built on modal superposition. As soon as say mode, you need frequencies. So let's insert a frequency case. We're going to use the same for restraint. We're going to use the same ones that we used in the static case right there. You know, one thing I would like to do is that see, all of these points should be moving. It will work, except that I'd rather also put a restraint here to make sure this thing moves in the x direction only. I'd rather do that. So let's go ahead and actually let me delete this. Go and select the user-defined restraint. That point, make it only move. Rotations are irrelevant because this is a beam element here. You can fix it, you can leave it. I'll fix it, and it can move in the x direction. Okay. It's just that sometimes if you don't restrain the some stuff, additional frequencies are going to pop up because of that lack of restraint. Okay, so let's make sure that this actually works. Again, static, nothing fancy. It's going to be exactly the same numbers as before. Right there, these are exactly the same number, I bet. Okay, and now we're going to do insert frequency case. Reference is the restraint that we put in there already. All right, and by default, it's going to give you 10 frequencies. 10 frequencies. Let's go ahead and find out what they are. Make sure that there are no things that we cannot recognize. Okay. Very good. Let's look at the deformation and double click on it. And these are all frequencies, and I hope because of the restraint that I put, they're all axial. There are no torsional, no bending, etc. I don't think there will be any torsional because this was treated as a bar problem. Yeah, good. Okay, now we can insert a harmonic transient dynamic, not harmonic dynamic, not transient one. Okay, for reference, frequency is going to be using the same numbers that we generated. We may have to use more of these. Now you asked for 10, but that's okay. Good. Now notice that I need a load excitation. Okay. Now what this thing, my load, the amplitude of the load, the way at least I'm talking about this particular problem, just look at this. The amplitude of my load is constant irrespective of what the frequency is. That need not be the case. In other words, it could be that a particular problem, the amplitude of the load depends on the frequency, which means that you have to introduce a modulation into it, frequency modulation. Okay, but in my case, it is constant. That being the case, I'm going to use white noise. Okay, so double click on the load excitation. First of all, the load is whatever I put in the static one, which is right there. The factor is 1. I'm not scaling it up. And for the selected modulation is going to be the white noise that I created. Now, as I said, if your amplitude, if your amplitude depends on frequency, then the white noise is no good. That means it's constant. And you have to go and create an Excel spreadsheet. The first column is going to be frequencies. The second column is going to be the amplitude of the load, but not in my case. All right. We're going to run it. Okay. So no big deal. Let's go ahead and generate a 2D plot. You're familiar with these things. Where you go? Next. Finish. It says go pick your node. Remember, it was node number 4. It was right in the middle. Let's see if we can find node number 4 here. I think it's... I may have to hide this. I don't know whether it's 3 or 4. Oops. I remember, maybe it was node number 3. I'm not sure. The middle point. Node. Okay. Good. Add. Now, Y and Z is irrelevant to me, although I can actually plot them, but it's totally irrelevant. They're 0, and then we say OK, close, and now we can look at our graph. You see for a second here, where is it that I plotted? Doesn't look right. Okay, so let's see now. This is in meter. First of all, let me change this thing to change this thing to inches. I keep forgetting how this. Okay, you have to put it in the white area. Okay, now it's inches, and it looks like the amplitude is constant over that range. Oh yeah, we haven't specified the range. One thing I forgot to do. Wow. Okay, let's go back here. Double click on harmonic response. 0 to not 10 hertz. 0 to I don't know, maybe 500 hertz. And how many points do we want? Let's say make it 100. And now look at the graph. Is that 500? Yeah, maybe that I have to go at higher frequency. Okay, so let's cancel that. Let's go back here. Let's go to 5,000 hertz because I have no idea what that. Well, let's check it out first. Ah, there. That range that you have to specify, how many seconds do you want to look at the result? In this case, what frequency it is. It's you have to put some intel. Well, we were showing the plot right here. It looked like the amplitude was constant, but here's the situation. I told you I'm going to come back to that peak and discuss it and this is time to do it. Now, what you have here is this is the resonant frequency. In other words, if the frequency of the applied load, that big omega, if it happens to match this frequency, and I bet this is the first frequency in hertz in the frequency that you calculated for axial deformation, then it's going to get you're going to get resonance. Okay, so let's go check something here. Let's check these deformations right there. You see that 2517 is the first axial natural frequency, and when the applied load frequency matches that, you have resonant, and that's what this peak is. Okay, so folks, I hope that you found this thing useful. As I told you, that this information is probably more appropriate in the context of that simply supported beam that I did with a cosine load. Okay, I could have done the same thing with this particular problem. Now, incidentally, theory says that if there's no damping, this is all going to go up. Okay, it's all going to go up. And in fact, let's do something here. Let's do something quickly. Let me make this thing maybe 6% damping. That's high. Okay. And let's run it. There, you see that? When you introduce damping to the problem, it reduces that infinite, in principle, infinite height into a finite height. I'll do another video segment on damping issues, and we'll worry about it later on. All right, so have fun with this.